In this lesson, we are going to talk about what's known as the central limit theorems for sample means. Now, there are different central limit theorems, but we're going to only focus on the central limit theorem for sample means. So before we get into the actual theorem, I want to give you some background understanding. We need to talk about what's known as a sampling distribution. So I want you to imagine that I find a sample. I pick a random sample. I'll call it sample 1. Okay, and then I find the mean of that sample. So I'll label that X bar and I'll put a little 1 down here to remind you that it's coming from sample 1. Then let's say I take another sample. We'll call it sample 2. And so I find the mean of that sample, and I'll call that X bar 2 so that we know it comes from sample 2. Then I take another sample. We'll call it sample 3. So I'll find the mean of that sample, and I'll call it X bar 3. Now, if I continue to do this a bunch of times, and all my samples have size n, okay, when I take all of those means out, so I take this mean, I take this mean, I take this mean, I take all the means of all of those samples that I find, and I create a new distribution where my variable x is all of those means. When I put all those means together and I assign it to this variable x, we have what's known as the sampling distribution. So now that we understand what a sampling distribution is, that's a new variable that we define as the means of each of these random samples that we're taking of the same size n. Now we can get into, now that we understand what that means, we can get into what the central limit theorem is. Now, the central limit theorem for a sample, if you're talking about specifically the mean, if you draw repeated samples over and over and over again of the same size, then the sampling distribution is going to be approximately normal. And as the sample size increases, we'll call it n generically, as the sample size n increases, the closer the sampling distribution gets to a normal distribution. Okay, so what this means is if I had all these samples that I talked about previously, sample 1, sample 2, sample 3, if originally I took sample sizes of, say, 20, if I repeat that process and I go ahead and take sample sizes of 30 or 40, and then I repeat it again, and then I start taking sample sizes that are 50, as those sample sizes that I take are bigger and bigger and bigger, this sampling distribution gets closer and closer and closer to that normal shape where you have the one mound and then it's symmetric. So let's take a look at our new notation. Okay, so if we have some random variable with the distribution, we'll call it just x. We'll call it any distribution. And the mean of that distribution is mu x, and the standard deviation, let me see. And the standard deviation of that distribution is sigma with your little sub x. then as the sample sizes that you take from that distribution over and over again, if that size n increases, then the random variable x bar will be normally distributed and it will have this notation here. It's normal, and it's going to have the same mean as the distribution that we're talking about. However, the standard deviation is going to change. You're going to take whatever the standard deviation of the distribution that we're talking about, and you divide it by the square root of n. That will give you the standard deviation of the sampling distribution. So that's this here. So this is the standard deviation of the sampling distribution. And then, of course, if you want to standardize it, normally before, when we were talking about in chapter 6, we would say z is equal to your data value minus the mean over your standard deviation. It's basically the same thing, but the notation is changing a little bit because your data value in this case, your value of x, is going to be a mean of one of those samples. Your mu is going to be the mean of your distribution that you're talking about, and then the standard deviation is going to be the same as the distribution x, but for the sampling distribution, you have to divide it by the square root of n. So it's almost the same thing with a few minor tweaks to it. Okay, so now let's go down and walk through an example, because this isn't going to start to click until you actually work through some examples. Okay, so we have, let's see, an unknown distribution. We'll call it x. And it has a mean of 90. So this is the mean of our distribution. And the standard deviation is 15. We're taking samples of size n is 25. And they're drawn randomly from this population. So if we take samples from this distribution, we know that it's going to be approximately normal, and that the mean is going to be the same, but the standard deviation is, because we're talking about a sampling distribution, is going to be 15 divided by the square root of n, which in this case is 25. We don't know if the distribution x is normal or not, but we do know when we do the sampling distribution based on the central limit theorem that it should be approximately normal, and it gets closer and closer to being exactly normal when the sample sizes get bigger and bigger and bigger. So we can make this approximation. Now, it says in part A, it says, what is the probability that the sample mean is between 85 and 92? So here are the key words here to let us know that we're looking at this distribution. We're looking at the samples, not the x's. We're looking at the means of the samples. Okay, so previously we would do this. We would say the probability that x is between 85 and 92. But this says we're looking for the probability that the sample mean is between 85 and 92. So just by that one word sample, that changes the whole problem. And instead of putting x is between 85 and 92, I'm going to make it x bar is between 85 and 92. Now, because we know that this is going to be approximately normal, we can use on the calculator normal CDF, and we put our lower limit, which is 85. We put our upper limit, which is 92. Then we put in our mean, which is 90. And we put in our standard deviation. In this case, because we're talking about the sample mean, we're going to put in the standard deviation is 15 over the square root of 25. That is the difference between looking at the sampling distribution versus looking at the distribution x. This is really the only thing that changes, the standard deviation. All right, now when we put that in on the calculator, we're going to get approximately 0.6997. For part B, it says find the value that is 2 standard deviations above the expected value 90 of the sampling mean. So if we imagine that this is our approximately normal sampling distribution of x bar, we know that the mean of the sampling distribution is the same as the distribution x, so I'm going to label that 90. Now the standard deviation for the sampling distribution we said was 15 over the square root of 25. Okay, now when I put this in on the calculator, I was lazy and just left it like that. But this is an easy number to calculate. If I take 15 divided by the square root of 25, the square root of 25 is just 5. So 15 divided by 5 is 3. So I know every time I make a mark to come out one standard deviation in either direction, I'm just going to be adding or subtracting 3. So this is going to be 93. This is going to be 96. This is going to be 99. I'm going to keep coming out and adding or subtracting 3. I'm going to subtract 3 going in this direction. That's going to give me 87. That's going to give me 84. This is going to give me 81. Now, if I'm looking for 2 standard deviations above the mean, that would be this value here. Because if I'm at the mean here and I come 2 standard deviations above, that's going to be 96. Okay, in this example, it says the length of time in hours it takes for an over 40 group of people to play one soccer match is normally distributed with a mean of 2 hours and a standard deviation of 0.5 hours. So all that information is given to us about the distribution x. So let's write this down. X is the time in hours. Okay, and then they give us that the mean of the x is, let's see, it says 2. And the standard deviation of x is 0.5. And they're asking us to find the probability that the sample mean, that's our x bar, not our x. Here's the key words right here. The probability of the sample mean. That's how we know we're using x bar here instead of x. Okay, we want to look to see if the sample mean is between 1.8 and 2.3. So because we're trying to find the probability about the sample mean, we need to use the sampling distribution. So with the sampling distribution and the distribution x, they're always going to have the same mean. The only thing that changes is the standard deviation. So if I want to find the standard deviation of the sampling distribution, x bar, I take the standard deviation of the distribution x and divide by the square root of the sample size. That is really the only difference between these two calculations. So now because we know that for x bar, we have an approximate normal distribution. Here's our information. Our mean is 2, and our standard deviation is 0.5 divided by 50. So to figure this out, to find the probability that the sample mean, your x bar, is between 1.8 and 2.3, because we know that that's approximately normal, we're going to use normal CDF on the calculator. We put in the lower bound. Here's my lower bound, 1.8. Then we put in the upper bound, which is 2.3. Then we put in the mean and the standard deviation, which is 0.5 over square root of 50. Okay, and we should get approximately 0.9977. So the probability that the mean of the sample is between 1.8 hours and 2.3 hours is 0.9977. Okay, in this example, it says in a recent study reported on October 29, 2012 on the Flurry blog, the mean age of tablet users is 34 years old. Suppose that the standard deviation is 15 years. We're going to take a sample size of n is equal to 100. And part A, it says, what is the mean and standard deviation of the sample mean ages? So we have two distributions that we're talking about here. We have the X distribution, and then we have the sampling mean distribution. For the X distribution, they give us the information in the problem about that. They tell us that the mean age is 34, and the standard deviation is 15. Now, for the sampling distribution, we know that the mean of the sampling distribution is going to be the same as the X distribution, which is 34. And then for the standard deviation of the sampling distribution, that's going to be the same as the standard deviation of X divided by the square root of the sample size. So that gives us 15 over 10, which is 1.5. So if we want to list out our answers for this question, our mean for the sample means is 34, and our standard deviation is 1.5. Part B says, what does this distribution look like? We know based on the fact that the central limit tells us as the value of n gets bigger and bigger, the sampling distribution will become approximately normal. This is a pretty big sample size, it's 100, but we also know that just in general, the sampling distribution is going to be approximately normal anyways. So we know that it's going to have one peak and it's going to be symmetric. And the center is going to be 34 for our sampling distribution, and our standard deviation for our sampling distribution is 1.5. We just found all that up here. And we know that it's approximately normal. So it's going to have one peak and it's going to be symmetric. Part C says, find the probability that the sample mean age is more than 30 years. So because it's asking about the sample mean, we want to see what is the probability that X bar, not X, but X bar is greater than 30. So when we look at our picture, 34 is in the center, 30 will be over here somewhere. If we're looking for the probability that X bar is greater than 30, we're looking for this. So our lower bound is going to be 30, that's this here, and our upper bound is going to be positive infinity, but we know when we use that on the calculator, we use 1e99. So we're going to put this in on the calculator. I'm going to say normal CDF, and we're going to put in the lower bound, which is 30. The upper bound is 1e99. And then we're going to put in our mean for the sampling distribution, which is 34, and our standard deviation, which we found up here to be 1.5. Okay, when we put that in our calculator, we're going to see that we get approximately 0.9962. Okay, last part in this question, it says, find the 95th percentile for the sample mean age. So what we're looking for, if this is our sampling distribution, we know our standard deviation is 1.5. We want to find the 95th percentile, meaning we want to find so that 95% is to the left of whatever that mean is. So when we're working backwards and we know the percentile, remember we have that inverse norm function on our calculator where we can put in the percentile as a decimal, and then we put in the mean and the standard deviation. If you forget where that's at, that's under the distribution menu, the same place where you get the binomial and the normal distributions. Look for inverse norm, and then you put in your percentile, your mean, and your standard deviation, and that will give you 36.5. So this right here, this value that makes that cutoff point would be 36.5, so that 95% of the data falls to the left. Which means also, another way to look at it is that 5% of the data falls to the right. Okay, last example in the section, we have that the mean number of minutes for an app engagement by a tablet user is 8.2 minutes. Suppose that the standard deviation is 1 minute, and we find a sample of 60. Part A says, what is the mean and standard deviation for the sample mean number of app engagement by a tablet user? Okay, so we have two distributions again here. We have X distribution, and then we have the sampling distribution, X bar. So they give us the information in the problem about X. They tell us that the mean is 8.2 and the standard deviation is 1, and this is in minutes. We know that the sampling distribution has the same mean as the X distribution, so we can say that that's 8.2. What changes is the standard deviation. That's going to be whatever the standard deviation is for the X distribution divided by the square root of the sample size. Now when we put that in decimal form, that's going to be 0.13. So here is the mean for our sample means, and here is the standard deviation for our sample means. Okay, part B says, what is the standard error of the mean? The standard error is the standard deviation for the sampling distribution, which in this case is 0.13. And what this tells us is it gives us an idea. Remember in general what the standard deviation tells us. It tells us how spread out the data values are. So this tells us, on average, a sample mean will be approximately 0.13 minutes away from 8.2 minutes, which is our mean. So that tells us approximately how spread out the data values are. And this is what it would mean in the context of this problem. And we're talking about it specifically. Remember, the sample sizes need to be the same. So we're talking about it specifically for sample sizes of 60. Okay, part C says we're going to find the 90th percentile for the sample mean. Okay, so if we look at a sketch of this, for the sample means, here's our distribution symbol, it's X bar. We said our standard deviation is going to be 0.13. Our mean is always the mean of our X, which in this case is 8.2. We want to find the value of X bar, what sample mean would give us the 90th percentile, meaning 90% of the values lie to the left. So using the inverse norm function on our calculator, we always put in the percentile, then we put in the mean, and then we put in the standard deviation. So we're going to put in this case inverse norm. The percentile is 0.90. The mean is 8.2. And then we put in our standard deviation, which is 0.13. And that's going to give us, let's see, 8.37. So that value right here at 8.37 is the 90th percentile, meaning 90% of the sample means that you pick from a sample size of 60 is going to be smaller than 8.37. Okay, and if you forget where to get this inverse norm, remember that's under the distribution menu on your calculator, the same place where you get the binomial, PDF, CDF, and the normal CDF. All right, part D, it says find the probability that the sample mean is between 8 and 8.5 minutes. So we're looking for this. We're not looking for X, we're looking for X bar because it's asking about the sample mean is between 8 and 8.5 minutes. So if we look at the picture of this, 8.2 is here in the middle, that's our center. 8.5 is going to be over here somewhere, and 8 is going to be over here somewhere. So we're looking for what's the probability that our sample mean is going to fall in that shaded area. Because we're dealing with sampling distributions, we know by the central limit theorem it's going to be approximately normal. And so we can use the normal CDF for this. We put in the lower bound, which is 8. We put in the upper bound, which is 8.5. We put in our mean, which is 8.2, and our standard deviation, which is 0.13. And then we hit enter. When we do that, we get approximately 0.9293. So the probability of a sample mean, if the sample size is 60, the probability that that sample mean falls between 8 and 8.5 is almost 93%, 92.93%.